Colloquium speaker today. So for those of you who might not know me, I'm Edlin Levine, and I'm a research associate in the department as well as a senior scientist at MITRE Corporation. I did my PhD here with Gene Golovchenko, and I had midway, third year, I decided I'd have the brilliant idea to go out and do an internship in industry, and that was when I joined Schlumberger Dole Research for a summer, and I was doing research with our colloquium speaker today, Dr. Robert Kleinberg. Now, when I met Dr. Kleinberg, he held the position of a Schlumberger Fellow, which in a company of over 100,000 people is a distinction which is held by maybe a dozen. Is that correct? And that is a tribute to Dr. Kleinberg's seminal contribution due to his pioneering research in not only the company, but also for the oilfield services industry in general. He currently holds the APS Distinguished Lectureship on the applications of physics, and it's in this capacity that I've invited him here today to talk to the department and to share his experiences in research at Schlumberger. And he is joining us from Columbia University and BU, where he currently does research on energy policy to address some of the critical areas of climate change. So I have a short bio, which I'll read, which is a little bit more detailed than perhaps I would say, and then I'll hand it over to you. So Dr. Kleinberg is a senior fellow of the Institute for Sustainable Energy at Boston University and senior research scholar at the Center on Global Energy Policy of Columbia University. Dr. Kleinberg was educated at University of California, Berkeley, a BS in chemistry, and University of California, San Diego, with PhD in physics. From 1978 to 1980, he was a postdoctoral fellow at the Exxon Corporate Research Laboratory in Linden, New Jersey. From 1980 to 2018, he was employed by Schlumberger and attained the rank of Schlumberger Fellow, as I said, one of about a dozen who hold this rank in a workforce of over 100,000. Dr. Kleinberg's work at Schlumberger focused on geophysical measurements and the characterization and delineation of unconventional fossil fuel resources. His current research centers on energy technology and economics and on the environmental issues connected with oil and gas development. Dr. Kleinberg has authored more than 100 academic and professional papers, holds 38 U.S. patents, and is the inventor of several geophysical instruments that have been commercialized on a worldwide basis. Dr. Kleinberg is a member of the National Academy of Engineering and is the 2018-2019 American Physical Society Distinguished Lecturer on the Application of Physics. So please welcome me in joining our colloquium speaker. Thank you, Dr. Kleinberg.
Okay, well, thank you, Edlin. Always a pleasure to be here at Harvard. If I look slightly familiar to you, if you've taken ES 231 with Michael Aziz, I lecture in that course every year on unconventional fossil fuels. And always a pleasure to be here and to be back in the physics department. So, as you see from the title of the talk, millikelvin to kilometers. How millikelvin physics is reused to explore the Earth kilometers below the surface. And what I'm going to present to you today is probably not a typical physics colloquium, but this is basically my charge from the American Physical Society that has asked me to sort of more or less go around the country and explain how graduate students or postdocs or undergraduates in the academic world can transition to what you might call the real world. And as this slide says, this is a fully worked out example of how one physicist made the transition from esoteric laboratory science to very practical real world inventions. By the end of this talk, you'll have learned how to measure which way the wind was blowing 10 million years ago and how to measure the sizes of pores in sedimentary rock and why that's all important. You'll also get a lesson in corporate jujitsu, which is the most important part of the talk. It's a slide in the middle, so stay awake. Your experiences will be different, those of you who have a prospect of going out into the real world. I adapted to my time and place, and you will adapt to yours. So this is where it all starts in graduate school. I studied at the time, newly discovered phases of the superfluid helium-3 below 3 millikelvin at University of California, San Diego in La Jolla. This photo is from a 1976 issue of Physics Today showing our laboratory. I'm seated sort of second from the right I appear to be lecturing my much more learned colleague Monty Crusius on some fine point of physics. But I'm sure this sort of scene is familiar to all of you. So this is where I got my basic education. Now, so why did I go into the oil industry? And when I graduated in 1978, I had a, I'd say, somewhat rocky, but more or less successful graduate student career. At least I graduated. That's perhaps all I can say for myself, really. And I didn't really want to go into the academic world because I could already see that becoming an assistant professor was really way too much work. With teaching, research, writing grant proposals, not for me. And the physical review letters that I wrote in graduate school had a devoted readership of about 10 people. And I really wanted to sort of play on a broader stage. So the big problem at the time, and this is back in the 1970s, was the fact that the United States was no longer producing enough oil to supply its energy needs. And there were two traumatic oil boycotts, one in the early 70s, one in the late 70s, which produced these long gas lines. Probably a few of the older people in the audience remember this very well, of having to wait in line for half an hour or more just to fill up your tank because some foreign country had decided they didn't want to sell oil to the United States. And so this really constituted what at the time was a pressing national need to establish some more energy security. Meantime, I was going to graduate school in San Diego. My housemates on La Jolla Shores Drive were, most of them were graduate students at the Scripps Institution of Oceanography, marine geologists. And I sort of got interested in geology by talking to them. And I also envied the lifestyle of being out on a ship for a month at a time, whereas, of course, I spent all my time in San Diego in the basement of the physics building, not seeing daylight for months on end, and that is literally true. So the combination of the pressing national need to develop more energy resources and the graduate school housemates getting me interested in geology led me to Exxon, where I had a 2-year postdoctoral fellowship. I worked there with Dave Waits, among others, and really liked the Exxon lab. But it was only for 2 years, and then I was out in the job market again, looking for another job. And the most attractive possibility that came up was with this company called Schlumberger, which is in what's called oil field service. In other words, after Exxon, whoever drills the oil well, Schlumberger comes along, lowers measurements into the well to tell you if there's any oil there, how much, how fast it can flow out, and all sorts of other stuff. So it's very instrumentation centric company. And that sort of worked in well with my graduate school experience as an experimental physicist. And again, the older members of the audience might recognize this Tektronix oscilloscope, which was a big part of my life back then. So that combined the measurements and the geoscience and the pressing national need all in one place. And that seemed like a very happy sort of situation. And indeed, it was a happy situation. So that's basically why I ended up where I ended up, basically responding to the needs and influences of the time. So let's sort of get into the science part. And first question is, which way was the wind blowing 10 million years ago? And you might think, how the heck can he find that out? I mean, the wind direction is very ephemeral. Generally when it stops blowing, you don't know where it came from. So what's the solution to that problem, and why do we care? So first, let's look at a simpler problem, which the importance of which is more obvious, and that is that you've drilled a well. Where do you drill the next well? And so what happens with these oil reservoirs is that hydrocarbon, which is less dense than water, which is pervasive in the subsurface, sort of is buoyancy segregated. So you underneath a layer of rock which is impermeable to fluid flow, oil and gas might be coming up from below due to geochemical processes I'm not going to talk about, but they segregate themselves into gas floating on oil, floating on water, as shown in the picture. And again, underneath an impermeable layer of rock, which traps the whole thing. If it wasn't there, it would all go to the surface and disappear. So the typical situation is that you've drilled a well and you drill and you hit nothing but water, which is very extremely uninteresting because these wells are deep. They're 1 to 3 miles deep. The water is highly saline. It's really a toxic waste. You don't want it, but you know that there's oil and gas floating above it somewhere. So where do you drill the next well? And the answer is that you drill toward the top of the dome structure. And which way is the top of the dome? Well, these rock layers sort of follow the dome structure. So if you can figure out from your 8-inch diameter borehole which way the rock is sloping, you drill upslope. It's called up dip. That's what the geologist would say. That's going to lead you to the top of the dome and the valuable hydrocarbons. So that's a motivation for getting some geometrical information about the rock surrounding the first well that you drill into a field. So how do you do that? Well, you do that with physical measurements that you lower into the well. But usually with physics experiments, you have a sample, you put the sample into a machine, and you can arrange your sensors and excitation equipment, whatever you like, outside of the sample, point it in. That's all well and good. We know how to do that. In the borehole case, the sample is outside of the machine and, in fact, is the earth. So what you're told when you start in a company like Schlumberger is that, okay, you can devise anything you want, any combination of signal generators, any combination of voltmeters or whatever, but it has to be inside a slender tube, no more than about 4 inches in diameter. It can be as long as you like, but it has to be in a slender tube that'll go down in a well, and you have to be looking outside of the tube. So again, the borehole that you're dealing with is typically 20 centimeters in diameter, 8 inches. The equipment has to go down anywhere from 1 to 10 kilometers into the earth as measured from the surface. So you think, oh, okay, interesting. But there are, of course, more rules than that. Because this is real field equipment and is not babied like what you have in the laboratory, the apparatus has to operate after being transported in Arctic, tropical, desert, or marine environments. It will probably be subjected to a 100G shock at some point in this transportation process. Somebody's going to drop the thing, right? And then it gets dragged through kilometers of rough rock borehole while you're making the measurement. The apparatus must operate while being exposed to temperatures ranging from minus 25 degrees centigrade in the Arctic to plus 175 degrees centigrade at the bottom of a deep borehole in salt-saturated water at pressures up to 140 megapascal. Again, sort of severe compared to your average laboratory. Temperature conditions are continuously changing as you move the instrument up the borehole. And you're making the measurement, by the way, while moving at 15 centimeters a second. You cannot stop and make a measurement, or at least there's a large penalty to stopping, and the clients really hate stopping because they want you to get out of the well, and so they can continue on because they're spending anywhere from $10,000 to $100,000 a day renting the rig that you're using. So it's not a science experiment. The equipment must operate at the end of 10 kilometers of multi-conductor cable, which carries nothing but power and telemetry, and autonomously and simultaneously with other nuclear, electromagnetic, and acoustic instruments, which are deployed at the same time. And so this is important. We send out the equipment with an engineer who's typically a bright guy with a bachelor's degree in engineering. But he has to manage the simultaneous data taking from as many as 6 instruments at a time. He cannot pay a lot of attention to your instrument. It's got to be really easy to use, easy to set up and monitor. Well, I'm a low temperature physicist. What the heck am I doing here? But the initial panic does subside. And I'm thinking about, okay, so we have to measure the slope of these rocks inside this borehole, how to do it. So of course, we physicists have our toolbox. So I thought back to graduate school with our, liquid helium at 3 millikelvin. No practical application for sure, but I thought back to the equipment they were building, and part of it was a magnetic susceptibility thermometry system. that is shown circled in the red. I'm not going to explain this whole diagram. It's all very complicated and interesting, but just focusing on the red oval, what it is it's a mutual inductance coil set, as shown in the lower left, with a primary coil that's excited by a oscillator, and then a balanced secondary coils counterwound with respect to the primary and each other, so that in the absence of a sample, you get zero voltage at the output. So there's zero mutual inductance between the primary and secondary. That's the idea. Now that mutual inductance coil set is unbalanced when you put in a small sample of paramagnetic salt, in this case cerium magnesium nitrate, which obeys the Curie-Weiss law, as shown in the lower left. So the susceptibility is directly connected to the absolute temperature, with two constants to determine, which we do routinely. So, okay, so I had this in mind as something I had built many of in graduate school, this idea of a primary and two secondaries unbalanced by the presence of a sample. But again, you're putting the sample inside the machine. So how do we measure outside the machine? So this is what I came up with. It's the same thing but turned inside out. So now we have a large coil shown connected to the oscillator I, which delivers a current I, which threads magnetic flux equally through two secondaries, which are counterwound with respect to each other. So in the absence of a sample, zero mutual inductance, zero voltage. The secondaries are unbalanced when they're brought near the borehole wall, which is somewhat conductive. Conductivity ranges from 1 to 1,000 ohm meters. And what happens is that the primary magnetic field generates ground currents in the earth, which then re-radiate a secondary field and stronger in one coil than another, and that's how you get the unbalance. And then you measure the voltage, and that is directly proportional to the conductivity of the formation. And I've already told you that conductivity can vary, that resistivity can vary from 1 to 1,000 ohm meters, so there's a big dynamic range that you have to work with to measure. So that's all good.
What is the wall of the tube made of?
I'll show you in a minute. In fact, it's on the next slide. So I'll show you on the next slide. So that's the basic idea. So here's how it gets worked out. This is a lab prototype of that kind of sensor. The coils are, because I really hated winding coils, it was absolutely the worst part of graduate school. I decided to make single-turn loops on printed circuit boards. That was easy. All you need to do is give them the mask. Okay, that's good. So these are all single-turn loops stacked up with various kinds of electromagnetic shields for technical reasons and put inside a metal housing, because you have to have a metal housing or else you will not survive all those horrible conditions I described to you. But the faceplate is protected by some very strong but non-magnetic and non-metallic material like alumina. I think in this case it was zirconia, actually, that we wound up using. Very tough non-metallic material, and that's the faceplate that the electromagnetic signals can get out. So this is what we built as a prototype. It would not survive dunking in a bathtub, but it was a electromagnetically accurate model of what we intended to build and deploy in boreholes. So here's a picture of the thing as it was eventually engineered. You had 4 of these sensors mounted on 4 arms 90 degrees apart in the azimuth, then lowered down into the well. The arms are sort of spring-loaded, so you can see the thing is bigger than 8 inches, but as you went into the well, the arms then pressed up against that 8-inch diameter borehole and pressed the 4 sensors 90 degrees apart onto the rock surfaces. So you had 4 of these sensors. So, okay, what is this thing doing? So, as I said, you make these measurements while moving at 15 centimeters a second, 6 inches a second. And now I'm showing a diagram of these 4 sensors positioned around the borehole. And sensor 1 is pointing to your left. Sensor 2 is pointing to your right. Sensor 3 is pointing to your right. Sensor 2 is pointing towards you. Sensor 4 is invisible. It's sort of into the board. And you can see that as this thing is moved up the borehole, it's encountering these layers of rock that have different electrical conductivities. So I'm looking at two layers, sigma 1 and sigma 2. And as you drag the thing up, sensor 3 first encounters the interface between sigma 1 and sigma 2, and you get a small displacement as shown on the sensor 1 track. And then a little while later, sensor 3 encounters that same interface, but a certain measured time later, by knowing how fast the instrument is moving and doing some easy trigonometry, you can figure out from those 4 measurements which way the Earth is sloping. In this case, it's sloping upwards to the right. And that tells you where to drill the next well. Aha, off to the right. So that's basically pretty simple measurement modality. Okay, so I promised you I'd tell you which way the wind was blowing 10 million years ago. So how the heck can I do that? So to answer that question, what geologists do is look at the landforms they see in the present day and then assume that there's going to be similar landforms that existed 10 million years ago, and those assumptions are generally pretty accurate. So what you see in deserts today are sand dunes, and there's a classic dune shape called the Barkhan dune. It sort of has horns that in the downwind direction. And interestingly, here's a cross-section of the dune. Wind drives sand grains up the back of the dune, the windward side. It sort of gets to the point, and then there's an avalanche at some point down the leeward or downwind side. And then maybe it rains or something happens, and you get layers of sand that are sort of fossilized. Now, you wouldn't think there'd be much electrical and then the whole thing is buried and then filled up with salt water, which gives you a conductive medium. Now, you wouldn't think there'd be much conductivity contrast between these layers, which are all made up of pretty fine sand. But in fact, because the measurement is pretty sensitive, you can, in fact, measure the electrical conductivity contrast between these layers, and then using the technique I just described to you, figure out which way these sand layers on the dune are dipping, and then you can say, okay, the downward direction is the direction of the wind. Why do I want to know that? Because if you drill into a sand dune and you're looking for oil and you find it, these dunes tend to propagate in the direction of the wind. So the best way to find the next dune is to drill downwind or upwind. But you probably would have a less likely to be successful if you drilled across the wind direction, because basically you're elongating the dune structure along the wind. So it actually has some practical importance to know which way the wind was blowing. It's not just sort of an interesting thing to know. Now, I promised you a lesson in corporate jiu-jitsu, and this is, I think, the most important slide in my talk. So pay attention. The instrument I just described, which eventually wound up making $150 million for my employer, was not the approach initially endorsed by management. They had a different idea based on acoustics, which I felt was not going to work out as well. So this project started as a skunkworks project after hours and on weekends, with me sort of working alone in the lab, putting together these coils as simple as possible. That's kind of what drove the simplicity, in part. After I got some initially favorable results, I was allowed to get a technician, and then after more favorable results, a theorist asked to join the team. So then it became 3 of us. And at that point, we were able to, actually have some substantial product. But our development group, which was in Paris, had their own ideas about how to make this measurement of the dipping rock beds. And so what I did was I built a copy of their device. I optimized it so it worked better than they got it to work. And then I showed that my approach was superior on a direct head-to-head comparison. So kind of won that competition. So the instrument was successful, and it saved our business in the most important oil field of the day, which was in the North Sea. So when we were done, and this whole thing took about 1.5 years. So when we were done, the technician and theorist and I had time on our hands. So how many of you have time on your hands on a routine basis, or ever? Probably never. But I'll tell you, it's that time on your hands that is the most valuable commodity you'll find in your career. And while the three of us had time on our hands, we invented that was something even more important, which is the subject of the second part of my talk. So the subject of part 2 is how large are pores in rock 2 miles below the Earth's surface? Again, why do you want to know? So what? So this is a picture of a rock. It's a Berea sandstone, which is a quarried sandstone from Kentucky, but it's very typical of the kind of rocks that you find in oil reservoirs. So you shouldn't think that an oil reservoir is some giant lake that exists in the subsurface like Jules Verne that you can drill into and sort of suck oil out of the lake. It doesn't work that way. The oil and gas is in very small pores in rock very much like this. So just to explain the picture, the white are grains of quartz, so this is sand, basically. The black are clay. Clay minerals often co-deposit with sand. And then the blue is actually blue colored epoxy, which has been infused into the rock to enable you to make a thin section, and that indicates where the pore space is, which can be occupied by water, oil, or gas. So the pore space is very important. Now, a key parameter in understanding oil reservoirs is how fast the oil is going to get out of this finely porous rock. And you can see these pores are, 10 to 100 microns, typical size. This is a very high quality rock. Oftentimes the pores can be much smaller. And the permeability of fluid flow in a porous medium is proportional to the square of the pore size. So it's really, really important to know whether your pores are really, really small, like submicron, or big, like 10 to 100 microns. That is worth orders of magnitude in the rate at which water or hydrocarbon will flow out of the rock and into the well. And of course, that controls your economics. So pore size squared, really important. So if you think about it, it's actually something that's really hard to measure. I mean, so you can imagine some imaging technique, but you don't want to be imaging in a borehole that's thousands of feet deep. I mean, there's just too many images. I mean, you can image a person, but the person's only 6 feet long. So this thing is like thousands of feet long. So you really want some sort of volumetrically average measurement that will tell you what sort of the mean square pore size is. That's the important thing. So sort of before I came on the scene, people thought that magnetic resonance would be useful for this. So just to very briefly tell you what magnetic resonance is, probably many of you are already familiar with it. But to do a magnetic resonance experiment, again, sort of laboratory situation, you put the sample inside the machine, you have maybe permanent magnets or a superconducting coil that gives you a strong, steady magnetic field, constant magnetic field called B0, which in this picture is horizontal, parallel to the magnetization of the permanent magnets. Then the second element that you need is some sort of coil or device that will give you an oscillating magnetic field that you can put on in pulses. That oscillating field is called B1, and it's vertical in the picture. The sample is sort of this green thing inside the coil. And then the third thing that you need is that the frequency of the oscillation has to be related to the strength of the steady magnetic field, horizontal field, through the gyromagnetic ratio. So that's the Larmor condition. So that's the three elements: strong steady field, oscillating field, and the oscillating field being a special frequency. That's what makes it a resonance measurement. So what does all this have to do with fluids in rock and pore sizes? So this is going to be a one-slide comic book version of how to measure pore size using NMR. So starting with box 1 in the upper left, you have this large steady magnetic field B0, which now is vertical in the picture, and that polarizes all the spins in the fluid. Now, we're interested in hydrogen. Hydrogen is abundant in both water and oil, sort of fortuitously, and so you polarize these hydrogen nuclei along the B0 direction. So that's step 1. Step 2 is that you put on that oscillating magnetic field that's perpendicular to B0 at the special Larmor frequency. And what that does is it tips the spins into a direction perpendicular to B0 with a certain pulse length and strength. And then the spin will precess at the Larmor frequency. Now, the interesting thing is that that precession in a plane perpendicular to B0 will continue regardless of what the molecule is doing. The molecule can translate, the molecule can tumble, rotate, whatever. The spin system doesn't care. It's completely decoupled from the molecular motion. Almost completely decoupled. Decoupled on the order of time scale of seconds, which is of course, huge long time. So the molecule is rotating, translating, and so on. Happily, the spin direction stays constant until the molecule hits a solid surface. Now, that solid surface could have a population of iron ion, which is paramagnetic, or manganese, which is these are both common in sandstones. And when it encounters one of those iron ions, then that gives you the possibility of energy transfer, so the spin can flip back to its happy ground state parallel to B0. And so by measuring the decay of magnetization with time, you can get some estimate of pore size. So for example, so here on the upper left is sort of, again, a cartoon rock with 3 different pore sizes, big, medium, and small. So in the big pore, it takes the fluid molecule longer to get to an interface where it might get relaxed. So let's call the relaxation time in that big pore 80 milliseconds, arbitrarily. In the medium-sized pore, the fluid molecules get to the surface faster, so the relaxation time will be shorter. Let's call it 20 milliseconds. And then in the smallest pores, maybe 5 millisecond relaxation time. And it turns out, and if you go through all the block equations and so on, this is pretty simple stuff, actually. What you expect to see is exponential decays of magnetization according to those three relaxation times I gave you. And because magnetic resonance is inherently a linear measurement, the amplitudes of those exponential decays, as shown in the upper right, are proportional to the volume of fluid cited in each of the 3 pore sizes. So you have the 3 exponential decays with amplitudes proportional to the volumes in the 3 pore sizes. And here I've shown that the 20 and 80 millisecond pore sizes have the same amplitude, and then the 80 millisecond has a higher amplitude. That all gets added up into what you actually measure, which are the black dots. And so the black dots are the data. You do an inverse Laplace transform to convert your multi-exponential decay into a spectrum of relaxation times, as shown in the lower panel. And what you find is 3 peaks, one at 5 milliseconds, one at 20 milliseconds, one at 80 milliseconds, with the area under those peaks proportional to the amount of fluid in each of the 3 pore sizes. So that's how you get a pore size distribution from NMR. Okay, so this is a cartoon rock. Let's see what a real rock looks like. So back to our Berea sandstone. And what we have is a continuous distribution of pores over 2 orders of magnitude in relaxation time, from, in this case, from 10 milliseconds to 1 second. And by doing calibrations, which is a big long story all by itself, you can relate those pore sizes linearly into, you can relate the relaxation times linearly into pore sizes, and the pore sizes run, as you see, from a few tenths of a micron to some tens of microns in that Berea sandstone rock. So there we have it. Once you have this information, then you can start doing some real permeability estimates, and smart people have done that. Okay, so all you have to do is build a magnetic resonance instrument that goes into a borehole. So, okay, I had done, in graduate school, I had done squid-detected NMR of liquid helium-3 in a completely bizarre experiment that could only be done at 3 millikelvin, basically. At Exxon, I had done conventional NMR of layered intercalation compounds. So I'd done NMR twice, and now I'm asked to do, okay, do this borehole NMR thing. How hard could it be? But again, you know, everything gets turned inside out. You can't put the sample into the machine because the machine has to go inside the sample. And now the picture is you can have any arrangement of magnets you want, any arrangement of coils you want, detectors you want, but it's got to, once again, fit into the tube. There might be a non-metallic window that's permitted, but basically it's inside a steel tube. And then that gets lowered into the earth with all the same conditions I talked about earlier. So, what to do? So, first of all, you have to forget the idea of putting the sample into the machine, so that gets X'd out. And let's just focus on the basic physics, the necessity to have the B0 field, the B1 field, the right frequency. How do you do it? So this is what I came up with. And the side view is shown on the left. So you can make the thing as long as you like. And in this case, it was 4¼ meters long, about 13 feet long, to have all the electronics, all the spectrometer, signal processing, telemetry, everything gets put into the 13-foot tube. At the bottom is the sensor section where you actually do the magnetic resonance. And the cross-section of that is shown in the bigger picture to the right. So what's happening here is that I have two magnets, which are slabs, magnetized in the direction facing out into the borehole. So you can imagine these two slab magnets, magnetization this way, which is projecting field out into the rock volume. That's where you need to make the measurement outside. And you can see that it's going to be radial into the formation. Now, if you think about those two slab magnets, which are long and thin, and reasonably thick this way, that's going to create a saddle point of magnetic field strength, which is helpful. So the field is going to be strongest directly in front of the pole pieces, the two north poles, and in between, the field will get smaller. And then, of course, as you go out, the field gets weaker as you get further from the pole piece. And when you sort of do the calculation, and this is fairly easy to do magnetic calculation, you have a saddle point of magnetic field strength, in this case about 500 Gauss. That's important because the saddle point gives you a finite volume to resonate at the right Larmor frequency. There's a B0 that occupies a finite volume that the Larmor frequency will apply to. So that's how we get B0. So B1 is basically created, and this was actually pretty inventive, with a coaxial cable that's split. So it's a long half coaxial cable with current running down the center conductor, up the outer conductor. That creates a magnetic field, which in the rock formation at that sensitive volume is perpendicular to B0. So there you go. Those are your two important geometrical conditions. You run the antenna at the Larmor frequency, and there you have your measurement. And that actually worked pretty well. So the whole thing is in a 13-centimeter diameter package. Once again, there's a non-metallic wear plate in front of the antenna. The magnets are packaged in metal housings so they don't fly apart. And that actually worked surprisingly well. The frequency is only 2 megahertz, which is, pardon me, which is lower than any commercial spectrometer that was on the market. So I had to build my own spectrometer, but that was fun. And that has gone out and made quite a bit of money for itself. So after it had been commercialized, I got this call from an oceanographic institute in California. So I seem to have some strange relationship with oceanographic institutes, which sort of launched my career. But they wanted to do NMR of a material called methane hydrate at the seafloor at a depth of 4,000 meters offshore Monterey, California. And I said, okay, well, tell me about the measurement. They said, well, it's really tough. You know, the pressure is 4,000 meters, so what is pressure? Is well under borehole pressures. Can't do that so quickly in my head. Temperature is 0 degrees centigrade. And I sort of laughed and I said, really, that's too easy because NMR likes low temperatures. This is lower than the temperature we're used to using. The pressure is nowhere near our maximum pressure, so no problem. Well, so here I am, 3 years, 3 years later, installing my magnetic resonance instrument, which is the gray structure, I'm kneeling, the gray structure sort of above my head. I'm installing it on their remotely operated unmanned submarine to go down to the 4,000 meters. And so measurement was successful, and the results were published in the Journal of Geophysical Research. So this was my NMR lab. This was the mothership for the submarine that we sailed out to do the experiment in. So once that was done, this whole idea of using NMR in strange field conditions sort of took on a life of its own. And the next adventure was on the North Slope of Alaska. So this picture is taken 13 miles from the Arctic coast. Again, I was using this portable NMR machine in sort of very strange conditions to measure properties of permafrost, and that was also published in the Cold Region Science and Technology. So, all fun. So, I just want to leave you with the thought that there are challenging and interesting problems to be solved in unexpected places, and that your physics education has provided you with a toolbox of techniques and skills that may prove to be useful in unexpected ways in the future. That was certainly true of me. But your experiences will be different. I adapted to my time and place, and you'll adapt to yours. So I'd just like to acknowledge my colleagues at the University of California, San Diego, in John Wheatley's group, and of course my Schlumberger colleagues over the years. This is an abbreviated list, but these are the people that participated in the projects I described. And with that, I'll just allow the remaining time for questions, and thank you very much.